Hello, welcome again to another tutorial, and this tutorial we are going to design a slab using the BS8110 codes. I hope I will enjoy the video, but as usual, I request you to kindly subscribe, like, and share my YouTube channel so that this knowledge can reach to as many people as possible. The question is, figure 4 shows a section through a concrete floor slab. The floor is subject to an imposed load of 3 kilonewton per square meter and spans between brick walls. Design the one-way spanning concrete floor given the following information: material strength, that is concrete strength, FCU 35 Newton per millimeter square, strength of steel, FY 460 Newton per millimeter square, concrete cover for all steel for mild condition of exposure, 20 millimeter, unit weight of concrete, 24. Then we have the table to use information from. Now looking at these, I think as we did the other one, we shall proceed. One, we obtain all the information given in the question. We have imposed load, 3 kilonewton, strength of concrete, strength of steel, wall thickness. And now here, they have told us it is one-way slab. Maybe just a quick recap, I would like to tell you that for a slab, we have, in terms of support, support here, I mean the distribution of load. We have a one-way and two-way slab. How do you know it is a one-way slab? Now, a slab has two dimensions. The longer dimension, we call it Ly. The shorter dimension, we call it Lx. When you compute the ratio of Ly over Lx and get a value greater than 2, we say it is a one-way slab. But when you compute the value of the ratio Ly over Lx and you get a value less than 2, we say it is a two-way slab. Now, the difference is here. So for one-way slab, the load is shared on two sides only. So this is the span. So you find this is a loaded area. Now the two beams carry the load. Now the Ly over Lx is greater than 2, but for two-way you find that is more of maybe two-way is something close to this. Now the ratio is less than 2, and you find that the load is distributed in form of a trapezium, So all the four beams carry the load. So this is the difference between one-way and two-way. This is a two-way. This is a two-way, meaning Ly over Lx is less than 2. So let us proceed. So we've been given the value. Now, if we've not been given the depth of slab, we shall start with the depth of slab. Now, under depth of slab, we start with minimum effective depth. Remember, effective depth is given as D. So the minimum effective depth for it, because our criteria here is a deflection criteria. Now, minimum effective depth is equivalent to span over basic ratio. Kumbuka, basic ratio for simply supported, we said it is 20. We had a table, we multiply by modification factor. Now, assuming I take modification factor as 1.4. Remember, in the previous tutorial, we said that the value of modification factor should be a maximum of 2.0. So this case, let me assume mine is 1.4, so that now my span center to center distance here is 4 meter, or rather 4,000 millimeter. It will be 4,000 over 20, which is basic ratio times 1.4. I have assumed this factor. Why? Because we said the value should not be more than 2. I get 142.86 millimeters effective depth. Now, remember, millimeter are very small measures. Now, we cannot have 142.85. Hence, now I shall assume my effective depth as 145 millimeter, right? I take now 145 millimeter. And then after that, I will assume diameter of main steel as 10 millimeter and cover been given as 20 millimeter. Now, let me show it to you. Actually, a slab and a beam is the same thing. The only difference, a slab has a B of 1 meter, and we call it a horizontal plate element, but a beam we call it a horizontal member, because a slab, the value of B is fixed to 1 meter or 1000 millimeter, but for a beam, it keeps changing. Now, remember what we did in the previous one. This is what we had. We had something of that sort. Now, if you recall, we had this. So this is what we call the overall depth. But if I have reinforcement here, now this measure from the top to center of main reinforcement is what we call the effective depth. Remember, up to the center of reinforcement. Now, from center of reinforcement to the end of reinforcement, I have diameter of over 2. Then from the outside of reinforcement to the outside concrete surface is cover. That is why this is H overall depth. This is D. That is why D is equivalent to H minus diameter of bar over 2 minus cover to reinforcement. Or alternatively, the other way around, the overall depth is equivalent to effective depth plus a half diameter of bars plus cover. Now, in this case, we have assumed that our main steel diameter is 10 millimeter. Now, this is how we shall progress. Now, from there, we can compute our overall depth of slab to be 170 millimeter. Then we can go to what? We can go to loading. Now, dead, we have self-weight of slab. Now, for slab is unique. For beam, we wanted to have a value in terms of kilonewton per meter. But for slab, we need a load in terms of kilonewton per square meter. That is why for the self-weight of slab, the value will be kilonewton per square meter. Now we take unit weight of concrete, which is kilonewton per cubic meter. We multiply by overall depth, which is meter in meter. Now, which will end up with kilonewton per meter square. So the self-weight of slab will be equivalent to unit weight of concrete times overall depth of slab, which is 4.08 kilonewton per square meter. Now, imposed load, QK is 3 kilonewton per square meter. Now, in reality, in the real practical world, this QK is normally determined based on the intended use of that particular house or structure. For example, you find QK, if you want to use that structure as a parking for vehicle, then the imposed load will be a higher value. If I want to use it like the structure is an office, imposed load I can use a smaller value. If it is for a dining hall, I use a bigger value. If it is a social room, a bar, is a higher value because I expect higher imposed load. So this value of imposed load purely depend on the purpose or what the structure will be used after construction. Now we go to ultimate load. Now ultimate load here, again, let us use capital W. Now, you have to be careful. Ultimate load here, I've said, for 1 meter width of slab, meaning my B is 1 meter or 1000 millimeter. The formula still stands. We have 1.4, which is a factor for K, 1.6, which is a factor for imposed or live load. Then we multiply. But remember, when we open, whatever is in the bracket is kilonewton per square meter. So if I multiply by 1 meter width, it remains kilonewton per meter. If I multiply by 4 meter, which is span, now it becomes kilonewton. That's how we arrive at 48.048 kilonewton, because 1 meter width takes away 1 meter, then 4 meter span takes away the remaining meter. Now we remain with kilonewton. Then now we move to design moment. Design moment, now because it's already a point load kilonewton, it will be WL/8. Like I told you, slab and a beam is the same design procedure, only that for a slab, B is 1 meter is fixed, but for a beam, it keeps changing. Now design moment M, WL/8, we have our W times L, which is our span over 8. We get 21.024 kilonewton meter, because it's a moment, ultimate moment of resistance. What the slab can withstand, 0.156 FCU BD square. Remember, FCU, strength of concrete. B is fixed to 1 meter, which is 1,000 millimeter. Then D, we calculated it from the assumption using the span, basic ratio, and modification factor. Now, this will be 0.156 times 35 is strength of concrete we are given. Then 10 power 3, this is B. This is 1,000 millimeters. Instead of 1,000 millimeters, I just have it as 10 power 3. Then 145 is our D. Now, this 10 power 6, as we did in the previous lecture, previous tutorial, is to convert from Newton millimeter to kilonewton meter. Now, in this case, which is the most cases, almost all slabs, MU, like ultimate moment of resistance, will be greater than the design moment, meaning no compression reinforcement is required. Nearly all slabs, no compression reinforcement is required. Then now we go to main steel. So for main steel, we'll say this way. For main steel, we know that K, that ratio, or rather coefficient, is given by M over FCU BD squared. Now we can substitute. Remember, M we have to multiply by 10 power 6 for conversion. We get that. Then our Z is equivalent to D into 0.5 root 0.25 minus K over 0.9, but must not be more than 0.95 D. Now for our case here, whatever is in the bracket is 0.96. Since 0.96 is greater than 0.95 D, we rule out that Z is equivalent to 0.95 D, which is 0.95 times 145. We get 138 millimeter. 138 millimeter. Now, AF is equivalent to M design moment divided by 0.95 FYZ. Remember, FY is strength of steel. Z, we call it arm length. We've calculated. So, if we substitute, we get 349 millimeters square per meter. Now, you have to be careful. If it is slab, the area is millimeter square per meter, because remember we said we are taking 1 meter width. Even the area, now look at the table 6. Table 6 say reinforcement bar area, millimeter square per meter width for various bar spacing. See, when you are dealing with slab, you cannot use the previous table of reinforcement. You have to use a table indicated reinforcement bar area per meter width for various bar spacing. So for this table, they'll be showing you the bar diameter and the spacing. So that is for a slab. Now our area is 349 millimeters square per meter. But remember, we have the minimum area for steel strength 460. Now, from the British code, BS81 code, it states that the minimum area is 0.13% BH, which means that our area we provide should be equivalent to minimum or greater than minimum. So if we compute minimum area here, now 0.13%, we know that if it's percent, it means 0.13 over 100 times B is 1000 millimeter, which is 10 power 3 times H is 170 millimeter, we get 221 millimeter squared per meter. Now, which is okay because our area is 349, meaning it is equal or greater than minimum area. Now, with this 349, we had assumed our diameter is 10. Now, let us come here. 20 for 10. Now we go to 10. So if we go to 10, we will move along this 10. We move until where we find a value equal or greater than 349. So if we move along this, fortunately we have an exact area, this one. So if I have this area, it means I provide H10 bars 225 millimeter center to center. So if it is reinforcement for slab, you must state the diameter and spacing, the bar spacing. So for this case, it is exact. We provide H10 at 225 center to center as main steel. Area of steel from the table, we get 349 millimeter square per meter. But we know spacing of bars will be lesser of. Now we compute 3D and 750 millimeter. Whichever is less, the spacing we provide should not exceed the smaller of the two. For this case, the smaller one is 3D. 3 times 145 is 435 because 750 is bigger. Now our spacing should be below or at most equal to 435. But our spacing is 225, which is very much okay. Now we have secondary steel. Secondary steel, others call them distribution steel or transverse steel. Steel is okay. Now, secondary steel is provided based on the minimum reinforcement area. Is provided based on the minimum reinforcement area. Minimum reinforcement area here we computed and we found it is 0.13 BH, which is what? 221. So I will go to my table. Because I want to maintain a diameter of 10 millimeter, I will come to my table. I will come here and move along 10 to see where I have 221. Excuse 221. So you find that I have 262. Then which means at 300 center to center. 300 center to center. That's where I ended up with the provide H10 at 300 center to center. AS is 262 because it should be more than or equal to the minimum area permitted by the code. Now we shall provide maybe, but we shall reach to reinforcement. So if this is my slab, maybe let me just illustrate. What we mean, main reinforcement are these ones. The one along the span this way, and then distribution, they do what? Distribution, they are in the other direction. They are going the other direction. So main reinforcement are normally at the very bottom, and then distribution or transverse are normally on top of the main reinforcement. But we shall see, we have a sketch of reinforcement detailing at the end. Then now we go to shear reinforcement. We go to shear reinforcement. So shear reinforcement, we say, now we know the slab is vertically loaded, which means RA is equivalent to RB, like end reactions are equivalent, and which is same as ultimate load divided by 2. Now ultimate shear force, V, we say this a pressure, is ultimate shear force over BD. Remember our B here is 1 meter or 1000 millimeter. Then our D is 145. Then we have to convert our ultimate shear force to newtons before we divide. So we end up with 0.145. And then now we go to design concrete shear stress VC. Let me remove this because it's making this area cloudy. Now design concrete shear stress. Now we say assume 50% of main steel is curtailed at support. Now curtailed at support, it means because bending moment is 0 at the support, the bars don't reach, all of them, they don't reach at maybe let me illustrate what curtailment means. So this is my slab. I have the reinforcement bar. So if I have my bar here, it will come this direction. If I have my bar here, it will, so from here, it will come, but it will stop at this point. Now we call them alternate bars reversed. Now my bar coming from my second bar will come from the end of this, but not reach the end of that. My next will come. So this is what we call curtailment. Why? This one will stop here, then this one will come here, because we know that design moment is maximum at the mid span, but it reduces toward the support until for simply supported, we know the bending moment is 0 at the support. So no need of wasting steel to run entirely from one end to the other. This is what we call curtailment, or we can say alternate bars reversed. Bar number 1 comes from opposite end, the other one opposite, but they don't reach the two ends. So each bar doesn't connect the two ends. It stops at some point. So now assuming there's a curtailment, it will mean that 100 AS over BD. Now this AS we had, the main area of reinforcement, we divide it by 2 because we're saying 50% of it doesn't reach what? The support. So it is only a half that is reaching. So we had, maybe to clarify, remember area provided was 349, but this 349, it is in form of reinforcement bar. And now, remember one bar reaches the end, the next doesn't reach. It reaches the opposite end, meaning that only 50% of the bar reach each end. That's why we divide the value by 2 to get 174.5. Divided by B is 1000, D 145, which is 0.12. Now we come to our table. Now let us come to our table. It says value of design concrete shear stress. Column number 1, 100 AS over BD. Column number 2, effective depth. Remember, effective depth is 145. 145 means we can use the column of 150 because it will be so difficult or time consuming to extrapolate. It's a waste of time. We can stick to the 150, effective depth of 150 because ours is 145. And then remember 100 AS over BD is 0.12. Now, which means it lies to equal or less than 0.15. Now, move this way. I will come here, my good people. We come here. We use this row here. We move and 150 is here. Why? Because our value is 0.12, which means less or equal to 0.15. And then now that effective depth here is 145, we can use this column for 50. We arrive at 0.43 Newton per millimeter square. But remember, the table value is for FCU 25. But our FCU is not 25, it is 35. Now we have to convert by taking 35 over 25 power third, all that we multiply by the value we obtain from the table, which is 0.5, 0.53. Maybe I put 35 because of for trend. For example, if you look at this, you find 150, D of 150 is 0.43, and D effective depth of 125 is 0.45. This means that when the effective depth reduces, the value of VC increases. That's why at 150 is 0.43, at 125 is 0.45. And because 145 is so close to 150, I just adopted a value of 435 just to add 0.05 for this 150 to make it that way. But now since it is 35, we take 35 over 25, all that power third times 0.435, we get 0.487. Now, since our design concrete shear stress, the capacity of our slab in terms of shear is greater than the shear stress coming from the applied load, then we don't need shear reinforcement. And remember, things you need to remember, one, almost all slabs, we don't need shear reinforcement. Almost all, practically all slabs, we don't need shear reinforcement. We don't need compression steel. Now we can proceed and check on deflection. So we can check on deflection. So we know the surface stress is given by 5 over 8, area required over area provided times strength of steel. Remember, strength of steel is 460, area required was 349, area provided 349. In this case, the two are the same. And then modification factor, we know the formula, it is 0.55 plus 477 minus service stress divided by 120 into 0.9 plus m over bd square, which will be less than 2. So, but remember we had assumed initially it is 1.4, but we can just confirm. So we have it is 1.38. So permissible span is 20, which is basic ratio for simple supported times 1.38, 27.6. Then actual, now they were to be the same. Why? Because it's like we worked backward. So they are to be the same. So in this case, the two are equal. So it is okay. Now reinforcement detailing is here. When you look at this, it is 14 H10 at 300. Now it means they will be, these 14 bars are the transverse. Transverse means they run perpendicular to the span. But now the main reinforcement, they run parallel to the span. For this case, this bar here, this one here, it is the main reinforcement, meaning that this is a span. They are running parallel to the span, but the distribution, these ones here, they are running perpendicular to the span. So they are here. So this one here, this H10 at 300 refer to this. And then this H10 at 25 refer to this because they are running parallel to the span. Thank you so much for watching. Keep the comments coming. Any questions, I will gladly respond to them. Thank you. Nice time.